Right, so let's make a start. If you're waiting, I'm sorry, you'll just have to wait for a minute. Okay, we're going to talk now about the production and properties of Ethyne gas. That's C2H2, Ethyne, C2H2. It is C triple bond C with two H's at each end. It is a symmetrical molecule. It is non-polar, and remember that a triple bond consists of one sigma and two pi bonds. Right? Triple bond is one sigma and two pi bonds. You should have done that already in organic chemistry, the theoretical side of it anyway. So let's look at the apparatus that we use for this. Let me just let these people in for a minute. Right, so the apparatus, there's a whole variety of apparatuses you can use, or apparati if you like, you can use. This is a micro apparatus where you make very small amounts, and that tends to make it safer. So what we have is, in a reaction vessel, which in this case is a boiling tube, we have some calcium dicarbide, CaC2, calcium dicarbide. You can also call it calcium carbide. That's absolutely acceptable. That's one reagent. The next reagent is, in the teat pipette here, is water, plain simple water. So with calcium dicarbide and we have water, when we react these two, we get calcium hydroxide and we get ethyne. Right? Calcium hydroxide and ethyne. You need to know that equation. The equation is sometimes written with one H2O and calcium oxide here. Don't just use this one. Learn this one and use it. Calcium dicarbide has lots of impurities in it, and some of these impurities can produce poisonous gases. So to remove those poisonous gases, we take the ethyne plus the impurities and we bubble it into some acidified copper 2 sulfate solution, which is blue. It bubbles through it. Notice that this pipe is below the surface of the solution. The gas passes through that, the impurities are removed. Ethyne goes along here, along this delivery tube in here, and we collect it over water. So the ethyne is collected up here. I'm sorry, I'm just checking to see is anyone waiting. There doesn't seem to be. Right, I'm not using the chat at the moment. Remember, you can contact me by email if you want to ask me questions. Otherwise, we'd be at it all day. Right, so ethyne, we can collect it over water. Why can we do that? It is non-polar. Water is polar. That's why we can collect it over water. So, right, so there's the equation again. Calcium carbide or calcium dicarbide plus water equals calcium hydroxide and ethyne. Right? Calcium dicarbide, you'll often be asked to describe it. It's a grey, lumpy solid. It reacts very exothermically with water. There's fizzing and lots of steam is produced as it reacts. So I just have to move a few things on my screen out the way a bit more. That's it. Right. So it reacts very exothermically, just like if you drop water onto a hot cooking plate or a hot frying pan, it goes and fizzes and splashes. Well, exactly that happens when you drop the water onto the calcium dicarbide. The calcium hydroxide that's formed here, right, is a solid. It's a white powder and it has a greater volume than the calcium dicarbide has. So that's something else to be noted. You could be asked that. Ethyne is bubbled through acidified copper sulfate solution. Why? To remove impurities such as phosphine, produced when calcium phosphide, Ca3P2, impurity reacts with water. Now you should know one impurity and what it's formed from. That can be asked, and it has been asked in the past. Right? Ethyne is a colourless gas and it has a sickly sweet smell. If you ever smelt it, you'd know what sickly sweet means. It describes it perfectly. Right? Ethyne burns in air with a very smoky yellow flame. Here we've got an evaporating basin or a crucible, could be either, and in it we've got some calcium dicarbide and we've put in some water and it's producing ethyne, and we light it and we get this very yellow flame, but we also get a very, very sooty flame, lots of carbon produced, right? So it's a very smoky yellow flame. If we put it in excess oxygen, we get a very, very hot flame, about 3,200 degrees centigrade or thereabouts, right? It produces an awful lot of energy, about 1,300 kilojoules per mole in terms of energy, and that's used to cut and weld steel. We call it the oxyacetylene burner or oxyacetylene torch for cutting steel. It's not a blowtorch. If you say blowtorch, you won't get the mark. And you have to be able to write the equation for the combustion of ethene. And remember, combustion means combining with oxygen. And if you do that, you're going to get carbon dioxide and water, because you get that for every organic chemical on our course. The only products of combustion are carbon dioxide and water, and then you have to balance it. Another use shown here is a lamp used by potholers. It's called a carbide lamp. You put calcium dicarbide here in the bottom. Up here is a tank of water. You let it drip onto it. It produces ethyne, or acetylene as its old name was, the old name for ethyne, and you light it here and it gives a very bright flame. So that's that finished there. So what we need to do now is I can't get to where I want to. We're going to look at the production of ethyne and some of its properties. You will get them on Schoology. I gave you the Schoology code before. If you haven't got the Schoology code, you can send me an email and I'll send it to you. Send the email to pjjsci@gmail.com. So here is what you would have. You have the chemistry, you've also got biology if you want it. And then we go down here to the practical videos. And we're looking for ethyne. There's ethyne there, so we click on that. Up it comes. We put it onto full screen and we play it. Now I'll stop this at 1 or 2 points so that we're pointing out things to you.
Experiment to prepare ethyne and examine its properties. C2H2 is prepared by the reaction of water with a substance called calcium carbide.
There's a calcium carbide there. Notice it's a grey colour, grey lumpy solid. This sort of browny bit, you can ignore that. That's because it's already reacted with dampness, moisture in the air.
CaC2. Calcium carbide is also called calcium dicarbide. Calcium carbide cannot be obtained in a pure state. It is usually contaminated with calcium sulfide, calcium phosphide, and calcium nitride. As a result, the ethyne obtained from it usually is contaminated with gases like hydrogen sulfide, phosphine, and ammonia. These gases are removed by bubbling the gas through acidified copper 2 sulfate.
Now here's the copper 2 sulfate. Here is the tube coming in. It's under the surface, and if you look, you'll see the tube going out up there is above the surface.
Set up the apparatus as shown. Do not touch the calcium carbide with your fingers, as moisture from your hands could start the reaction. Use the spatula when transferring the calcium carbide to the flask. No naked flame should be brought anywhere near the gas preparation apparatus. Ethyne gas forms an explosive mixture with air. Tests on the gas should be performed well away from the apparatus.
Making sure that it's sealed well, because water in the atmosphere will react with the calcium dicarbide. So there he's adding the second reagent, water, into what we call a dropping funnel.
Double check that you have connected the gas washing bottle correctly.
Sorry, let's go back a tiny bit.
Double check that you have connected.
Right, there you can see this is a Buchner flask with the side arm coming out. The gas comes out here, goes down this pipe into the acidified copper 2 sulfate, comes back out and escapes through this pipe here, and then goes into what we call a trough of water. It can be a large beaker, it doesn't matter, but it's filled with water.
Is the gas washing bottle correctly? Using the dropping funnel, add water slowly to the calcium carbide to maintain an even, not too vigorous evolution of ethyne.
It's actually quite difficult to control it. You can see how rapidly it reacted there when the first drop went in. Now he's got it going drop by drop. That's what he wants to do.
Collect some test tubes and a few gas jars of the gas.
When you collect a gas, it's normal to throw away the first container full, because what happens is, before you start, this and the delivery tube are filled with air. The gas is formed, it pushes the air out, and then it can be collected. So the first test tube or the first gas jar is usually air. So you usually throw away the first one, and then the ones after that are pretty pure. We've got it going nicely, nice and steadily. Look at the gas, it's colourless. It's also clear, but don't call it clear, call it colourless. When it's full of gas, you will put the gas jar lid on. It's just a sheet of glass, but we'll have Vaseline on it to make the seal good. We'll put that away and put on a new one. It should actually be sealed under water rather than out of water, as he did there. if you look, you can see the whitish calcium hydroxide here, and you can see that it's actually swollen up.
The equation for the reaction is shown on the screen. Note the formation of white calcium hydroxide inside the flask. Place your hand on the outside of the flask. When you perform this experiment yourself, write down what you notice.
It will of course be very hot because it's a
In the next part of the experiment, we will carry out a number of tests on the gas. Note the physical properties of ethyne. It is a colorless gas with a smell. If impurities are still present, it will not smell very nice. Like methane and ethyne is insoluble in water, but soluble in organic solvents. Combustion. If your teacher allows it, bring the gas jar of ethyne to the fume cupboard. Remove the gas jar cover and apply a lighted taper to the mouth of the gas jar.
See how smoky it is?
Note that it burns with a luminous smoky flame and a great deal of soot is formed. The soot is formed as a result of unburnt carbon. Addition of bromine. As in the case of the preparation of ethyne, bromine can be used to test for unsaturation. Add about 1/10 of a test tube of bromine water to a test tube of ethyne. Replace the stopper and shake the test tube a few times. Note that the yellow color disappears. The very reactive carbon-carbon triple bond reacts readily with the bromine. You are not required to know the equation of the reaction or the names of the products for this course. Addition of...
It was yellow before, or I would always say red-brown before. Doesn't matter what it looks like, call it red-brown, and it becomes colourless, not clear, it becomes colourless.
Of acidified KMnO4. As in the case of the preparation of ethyne, potassium permanganate can be used to test for unsaturation. Add about 1/10 of a test tube of potassium permanganate to a test tube of ethyne. Replace the stopper and shake the test tube a few times. Note that the purple color disappears and a colorless solution is obtained.
And again, colourless. It goes from pink or purple to colourless, not clear.
The very reactive carbon-carbon triple bond reacts readily with the potassium permanganate. You are not required to know the equation of this reaction or the names of the products for this course. Hence, it will not be discussed further. This concludes the study of the properties of ethyne.
Right, so let's get back to this. Right, just a point here actually. Let me just see. If you go to the Schoology, you will find there this. Right? This is what I call my organic synthesis summary. So let's just look at it. We have just made ethyne by reacting calcium carbide with water to give us ethyne and calcium hydroxide. That will give us an alkyne. It will give us ethyne, and the functional group of ethyne is C triple bond C. Right? We can test that for unsaturation by reacting it with bromine. It will give us 1,2-dibromoethane, and it will decolorize it. And don't forget, if ever you talk about changes of colours, give the starting colour and the finishing colour. We looked at how to make an alkene, and again we can test it for unsaturation. We can change an alkyne to an alkene by adding an addition reaction, by adding hydrogen gas H2 and using a nickel catalyst, and we could put in heat there if we wanted, 410 degrees centigrade. Now, you should print this off and learn it. Right? This is a summary of the whole organic chemistry course. Right? So what we did earlier too is we made an alkene, we made ethene by an elimination reaction, removing water from ethene using the catalyst and dehydrating agent aluminium oxide and heat. So that turned our primary alcohol into an alkene. Right? Now we're going to talk about turning an alcohol, a primary alcohol, into an aldehyde. This is an oxidation reaction. That's the type of reaction it is. To do that, we need H+. H+ is what acids are. We'll see that a bit more again in a minute. Then we use dichromate. It can be sodium dichromate or potassium dichromate and heat. We are no longer allowed to use dichromate in the lab, so you don't have to know about that, other than that's how you do it and that it is oxidation. That will give us an aldehyde. Primary alcohols give us aldehydes by oxidation. Secondary alcohols give us aldehydes by oxidation. The conditions are exactly the same. It's just that it's a secondary alcohol. The secondary alcohol is one where the OH, the carbon to which the OH is attached, has two carbons attached directly to it. A primary alcohol, the carbon which has the OH attached to it, only has one carbon attached directly to it. So if we have a primary alcohol and we oxidize it, it gives us a ketone. With an aldehyde, it will oxidize further and become a carboxylic acid, right? And the same conditions will apply. But with the ketone, it doesn't oxidize further. It stays exactly where it is. Now, so that's a very, very useful table to learn. Right, so we've talked briefly about making an aldehyde from an alcohol. Here is ethanal. This is ethanal, the second member of the aldehyde series. Right? Made by the oxidation of a primary alcohol, ethanol, to make ethanal. It smells of rotten apples. If you meet someone who's been drinking a lot the night before, there's a particular smell off their breath the following morning. The smell you get off their breath is ethanal. Right? Where did the ethanal come from? It came from their liver. What the liver does is the liver detoxifies, it takes away poisons, and what it does is it turns the poisonous alcohol into the less poisonous aldehyde, and it can be removed. Right? So it's the liver protecting you, but it gives you the characteristic smell of someone who's been drinking. Right? Short chain aldehydes are soluble in water. Why are they soluble in water? Well, they have the carbonyl group. That is this C double bond O group at one end. And so if they've got the carbonyl group, they will be soluble. In the case of ethanol, it makes up about 50% of the molecule. But if I had 7 or 8 carbons in a chain here, it would be much less important. So that's the carbonyl group. The carbon end is delta plus, and the oxygen end is delta minus. What delta plus and delta minus mean are a small bit positive and a small bit negative. Right? So long chain ones are insoluble in water because the polar carbonyl group is a less important part of the molecule. Right? How do we show that aldehydes are aldehydes? How do we test for them? Well, you can use 2 tests. There are 2 possible tests you can use. One is you can mix Fehling's 1 and 2 solutions. Some people call them Fehling's A and B. Then you add the aldehyde. Now, the reason we say we mix these is because you have to mix them and then use it pretty much immediately. Right? Then you add your aldehyde, and of course you mix it, and then you heat it gently, usually in a water bath, and it turns from blue to red, right? It turns from blue, here it is before, and here it is after, right? So blue to red. Now I know you could call it brown and that would be okay, right? But if we call it a red precipitate, this is in fact, the blue is caused by copper 2 ions, and this is caused by copper 1 ions. That doesn't really matter to you, right? The second test is what we call Tollen's silver mirror test. Tollen's silver mirror test. You mix the thing you think is an aldehyde with a solution called ammoniacal silver nitrate. That's a mixture of silver nitrate and ammonia. In the video we'll look at in a second, you'll see how it's made. You don't have to know how it's made. You can call it either ammoniacal silver nitrate or you can call it Tollen's reagent, right? And when you do that, it produces a silver mirror on the inside of the test tube. The test tube must be absolutely clean, or else instead of getting silvery silver, you'll get silver oxide, you'll get black silver. You can see up here at the top, it's actually slightly oxidized there. So this is how they used to make mirrors. You would take ethanal in solution, you would add Tollen's reagent to it, and you would heat the glass from underneath. That would cause the silver to deposit on the sheet of glass. You would then pour off the aldehyde and the ammoniacal silver nitrate. You would wash the glass with deionized water, and then you would dry it, and immediately then you would cover it with a layer of tar. So I'm going back 100 years ago now. And the tar would be there to stop air reacting with the silver. If you have a silver trophy on your mantelpiece or a silver ring or silver cufflinks and you leave them sit for a long time, they go black. And that would happen to the silver in the mirror. It would oxidize, it would tarnish. So that's why they covered it with pitch to stop the air getting at it. So that's that. Ketones, just a brief word about ketones. Ketones are made by oxidizing secondary alcohols, right? Using acidified dichromate and heat, the same as with the aldehydes. Unlike aldehydes, they do not oxidize further. So they do not show reactions with Fehling's or Tollen's reagent, or indeed with potassium permanganate, right? They can be reduced, they can, in other words, turn back into a secondary alcohol using hydrogen and a nickel catalyst and heat. And that turns them back to the secondary alcohol they were derived from. So let's just have a look at the video that goes with that. The beauty of these videos is that you can watch them as often as you like. Where is it going? Reactions of ethanol, there we are. Now they'll show you ethanol and they'll show you a ketone, propanone as well.
To study the reactions of ethanol with A. acidified potassium permanganate solution, B. Fehling solution, and C. ammoniacal silver nitrate. In this experiment, we will study how ethanol reacts with the compounds listed. A. Reaction of ethanol with acidified potassium permanganate.
I don't think you have to worry about this, but potassium permanganate is a powerful oxidizing agent. So it will oxidize an aldehyde and turn it into a carboxylic acid. That's what it will do.
Add about 5 drops of ethanol to about 1/5 of a test tube of acidified potassium permanganate.
The amounts don't matter.
Using the test tube holder, stand the test tube in a beaker of hot water for a few minutes. Note the color change and with the aid of your textbook, explain your observation. Repeat the experiment with propanone.
ketone, and the ketone won't be oxidized. Ketones don't oxidize further. That's why the ketone will have no effect there. That's never been asked, and I don't think it will be asked.
Note that there is no color change. With the aid of your textbook, explain why there is no color change in the case of the ketone.
It doesn't oxidize. It doesn't reduce the potassium or manganese.
This concludes the first part of the experiment. Part B. Reaction of ethanol with Fehling solution. Make up some Fehling solution by mixing about 1/10 of a test tube of Fehling's A with the same quantity of Fehling's B.
Again, A and B, 1 and 2 doesn't matter. You don't have to know that 1 is blue and 2 is colourless. You just mix them together, and then you add your aldehyde. So there's Fehling's A and Fehling's B.
The mixture should be a clear royal blue colour. Add about 5 drops of ethanol to the test tube containing the Fehling solution. Using a test tube holder, stand the test tube in a beaker of hot water for a few minutes.
Blue, watch it. So it's now gone red. Call it brown if you like.
Write down what you observe and explain your observation. Write down also the 2 half reactions taking place. Repeat the experiment with propanol.
You do it with propanol, nothing happens. It doesn't oxidize. You shouldn't do that. You shouldn't split stuff back into a bottle. That's bad laboratory practice. Just to answer the question from the last bit of the thing, the change in colour is that copper, copper 2, Cu2 plus, is reduced to copper 1 plus. Copper 2 is blue, copper 1 is red. And if you mix blue and red, of course, you get brown. That's why it, for at least part of the time, is brown.
No colour change. With the aid of your textbook, explain your observation. This concludes this part of the experiment. Part C. Reaction of ethanol with ammoniacal silver nitrate, the silver mirror test. To 1 centimeters cubed of a solution of silver nitrate, add 1 drop of dilute sodium hydroxide solution.
Now he's telling you how to make it up. You don't need to know how to make it up. All you need to know is the result of the test. You should be wearing rubber gloves as well, because silver nitrate is nasty stuff. It will turn your skin black. Again.
A brown precipitate of silver oxide is formed. Add dilute ammonia solution drop by drop until the brown precipitate just redissolves. You have now prepared Tollen's reagent. Tollen's reagent must always be freshly made up. If stored, it is likely that explosive products will be formed.
That's worth remembering if you become a teacher.
Take another dry test tube that has been washed out thoroughly with detergent, rinse with ordinary water, and finally with propanone to remove any droplets of water. Pour the Tollen's reagent into the clean test tube.
All of that is just to say you take a clean test tube.
Add about 3 drops of ethanol. And using a test tube holder, stand the test tube in a beaker of boiling water for a few minutes.
Doesn't have to be boiling, just has to be hot.
Note the formation of a silver mirror on the inside of the test tube. No silver mirror is formed in the case of propanone. Using your textbook, explain why this is the case.
Ag plus in the silver nitrate is reduced to Ag, the silver metal. Right, so we'll make a start on the carboxylic acids and we'll finish them off next day. Right, so let's make a start on it with 5 minutes left. So, right, carboxylic acids. How do we know a carboxylic acid? It ends in COOH. Right? It ends in COOH. That's a functional group. That's a group of atoms that makes carboxylic acids behave like carboxylic acids. So what do we have? We've got C double bond O, that's a carbonyl group, and we've got a hydroxyl group here. Both of these are polar. So this is quite a polar thing. The R here can either be hydrogen, in which case that would be methanoic acid, having just one carbon, or it can be an alkyl group. If it's a methyl group, that's CH3, this would be ethanol. Right? So R can be an alkyl group or hydrogen. Right, names of the carboxylic acid. The first one is called methanoic acid. HCOOH is its chemical formula, its molecular formula. It's commonly called formic acid. Why is it called formic acid? Because it was first discovered by fractionally or distilling ants. And it came off of ants. Ants belong to the genus Formidae, so this acid came from ants. That's why it's called formic acid. It's nasty stuff. You will have come across it, probably not as a sting of ants, because I don't know too many people who have been stung by ants, but I think everybody has been stung by nettles, and the sting of nettles is caused by formic acid. The tiniest little drop of formic acid can produce those big blisters on your legs or on your arms. Right. The next one is ethanoic acid, CH3COOH. Ethanoic acid is what we call vinegar. It's also called acetic acid. And Other carboxylic acids you have to know about: propanoic acid, right? Propanoic acid, COOH tells us it's an oic acid, and we've got 2 and 1 3 carbons. Therefore, that is propanoic acid, 3 carbons. Butanoic acid, 4 carbons, 3 and 1. Don't forget to count this carbon, right? And then another one we have to know about is benzoic acid. Benzoic acid, C6H5COOH, because we'll be making it later on in this course. And if we look at benzoic acid, there is the structure of benzoic acid. Right? The H of formic acid has been replaced by a benzene ring. So we've got C6H5. Each carbon has 4 bonds. This one has 1, 2, and part of this thing here, which is called a delocalized pi bond. All the 6 electrons are shared equally amongst the 6 carbons for that bond. This one has got 1, 2, 3, and a hydrogen off here, 4. This one, 1, 2, 3, and a hydrogen off here, 4. 1, 2, 3, hydrogen 4. 1, 2, 3, hydrogen 4. 1, 2, 3, and the bond to the carbon 4. That's why it's C6H5COOH. Right? So count the C of the COOH in the name. Right? Let's just talk briefly about the physical properties. Right? The melting points and boiling points of carboxylic acids are higher than expected for the molecular masses. Why? It's due to the polar nature of the COOH group, which leads to hydrogen bonding. Hydrogen bonding makes the molecules stick together more. You'll have come across it if you do biology. Hydrogen bonds hold the 2 chains of nucleotides together in DNA. Concentrated ethanoic acid's melting point is 18 degrees. So if you keep it in a cold room, it will solidify. When you do, it looks like ice. So we call it, or it's called commonly glacial, meaning looking like ice when it's solid, acetic acid. Right? Shorter chain members are soluble in water due to the polarity of the COOH group. Right? So I think we'll leave it at that for today. Thank you very much for attending, and we'll see you on Thursday of next week at 11 o'clock. Please sign in early. Right, goodbye now.